Hey everybody, we're quickly approaching the end to the 2019-2020 e-learning experience, which sadly means we're approaching the end of honors physics for high school. I know it's a sad time for you because of that. But anyway, I want to do one last video, a little less academic, a little more interesting maybe. You're still going to learn some things, but we're just applying concepts that you already know. So hopefully you'll find it more interesting. This light unit, there's a lot of things in light that you see every day of your lives, and maybe some of the things you've thought, I wonder why that happens that way, or maybe you haven't thought that, but we're going to look at some of those things right now. First up is something you probably don't see every day is, I call it, how deep is the fish? When I was a kid, I remember going to a lake and looking in the water, and I could see all these fish down there, and they looked like they were right at the surface. Like I could just reach in and grab them. So, of course, I tried to do that. And of course, I didn't catch any fish. One reason is they were probably too fast for me. But the other reason is I didn't understand refraction at the time. Let's look at this. Okay, this picture is a little fuzzy. I've got a couple fuzzy pictures in this video, but they're good. I like them, so I'm using them. Anyway, we've got a cat looking into the water at the fish. Now we've got light coming off or reflecting off the fish, and then it's going from the water to the air. So we know it's going to bend. It refracts. It's going from a slower medium to a faster medium, so it's going to bend away from that normal line. So when this cat sees the fish, this cat sees the light coming from the fish in this direction. So it appears the fish is actually at this location. So the cat's going to jump in there at that location because cats love water. And the fish is going to laugh and swim away, and the cat will be mad and all wet. But refraction is causing the fish to appear at a different location than it actually is. Similar when the fish is looking at the cat looks higher in the air than it actually is. Here's another picture, same concept. A fisherman sees a fish in the water. But if there's no water, if you look at the direct line of sight between the fisherman's eyes and the fisherman shouldn't be able to see the fish, but because of the water and that refraction, he's able to see the fish. Mirages. So mirages, I'm talking about the ones you may see on cartoons where they're in a hot desert, they're really thirsty, they see a lake off in the distance, so they go running towards that lake and they take the water, they splash it on their face and their mouth, and all of a sudden, it's not water, that's sand, but it looked like water from a distance. That's what I'm talking about. Now, these mirages, they're actually real. Some people say they're just hallucinating. No, they're actually real. So here's a couple pictures. One is in the desert. Looks like there's water on the desert ground out off in the distance. The other, you're going to see this all the time. Now that you're driving more, the weather's getting warmer. You need a warm day to see this, really. But up ahead on the road looks wet, but it's not wet. You get up there and you notice it's not wet. So what causes this? Okay, so the light coming from the sky, normally it would just come straight to you like this. But on a hot day, here we've got like a desert, same applies to a hot road. The air above that surface is very hot as well. So the light is coming from a cooler situation. The air is cooler up here to a hot air situation. And it's not an instant change, it's a gradual change. So as the light is going from the cooler air to the hotter air, it's essentially a change in medium. That light is going to refract, it's going to bend. When it goes to the hot air, again, it's a gradual change, so it kind of gradually bends like this. Now this is exaggerated. Really, you'd be looking more off in the distance. The angle wouldn't be as steep, but you get the idea. So when the light hits this person in the eye, it's coming from this direction. So they see this image over here on the ground. That's an image of the sky, actually. Our whole lives, we've never seen the sky on the ground, so we never think about that. When we see something like that on the ground, we think, oh, I've seen that before. That's a lake or a pond. Well, it's not. It's really an image of the sky. Here's another atmospheric refraction. When you look up to the sun as it's setting, it's actually not where it appears to be. The sun's rays come into Earth's atmosphere like this, and Earth's atmosphere, it gets more dense as you get closer to the ground. So we are basically at the bottom of a lake, but instead of water, it's air on top of us. So it's more dense down here. So similar concept, the light ray is going to bend. You've got a gradual change in medium. So you're going from a faster medium to a slower medium, gradual change in medium, so it's going to bend like that. So when the light hits you, it's coming in at this angle, so it looks like the sun is actually higher in the sky. So at a sunset, the last little bit of sun that you see right before it goes below the horizon, that's actually already below the horizon. You shouldn't be able to see that if there weren't that refraction. And you shouldn't be able to see it because Earth is round. Here's another mirage. This is a little hard to see, but what this is we're in Michigan, and that is the Chicago skyline that is upside down. Yeah, upside down. So how does that work? So it's a similar concept, but over the water, you've got cooler air, and then higher above, you've got warmer air. So the light reflecting off the skyline, or in this case, the sailboat, gets refracted due to that difference in medium, and it comes in into you like that. So again, due to the geometry of Earth, you shouldn't be able to see it, but due to this refraction, we can see it in its case where it just flips the image upside down like that. Diamonds. Okay, diamonds. People like diamonds. Why do they like diamonds? Because they sparkle. Why do they sparkle? Have you ever thought about that? Check out this demo. All right, I've got two rings with me. One is this nice piece of costume jewelry. Very big, very cheap. The other is my wife's diamond ring. Much smaller, not so cheap. And I've got a laser pointer with me too that the cat and the dog both love. Now, one reason why people like diamonds is they sparkle. And when you go to buy a diamond, you have to know the 4 C's for diamonds. First, carat weight. That's how big the diamond is. Second, color. That's what color the diamond is. Third, clarity. That's how clear the diamond is. And fourth is cut. Cut is extremely important for diamonds to get that sparkle. So I'm going to shine the laser pointer first in the costume jewelry, and you're going to be able to see the sparkle on me. Okay, now I'm going to take the real diamond ring. A lot more sparkle with the real diamond, a lot more total internal reflection. That's what makes it pretty. I love sparkly diamonds. So we saw the real diamond had a lot more sparkle than the fake diamond. Let's take a look at why. When you have light coming into the diamond has a very high index of refraction, which means it has a very low critical angle. So a lot of that light coming into the diamond, once it's in the diamond and it hits the back face of the diamond, a lot of that is beyond or above the critical angle. So you get total internal reflection, and it'll reflect over here again because diamond has a very high index. It's a lot of it is above the critical angle. So again, total internal reflection, it comes back out. So the fake diamond has a lower index of refraction than a real diamond. So you won't get as many of the light rays being reflected back out. A lot of them are going to go through, and that's why it doesn't sparkle as much. Now, in terms of the cut, here's an ideal cut. You've got a lot of that light is going to exceed that critical angle and be reflected back out and make it sparkle like that. If the cut is too deep, you may get the first hit here at the backside exceeding the critical angle. It'll reflect, but then the second one, where less than the critical angle, it comes out the side. Or if the cut is too shallow, it'll just hit the back and go through and light up your finger. So anyway, when you go to buy a diamond, make sure you take with you a laser pointer, and then they'll hand you the diamond. They always let you handle them, and then ask them to turn off the lights. That shouldn't be a problem. And then shine that laser pointer into the diamond, and then look at the ceiling, count the number of red dots. The more red dots, the better, because that's more sparkly. Rainbows. We've all seen rainbows. Usually you see them at the end of a storm. Or if you take the garden hose in the backyard, you put it on the fine mist setting, a lot of times you can see a rainbow that way. Or you can go to the big island of Hawaii. Here we have what's called Rainbow Falls, appropriate name for it. It creates a lot of mist in the air, and for a good part of the day, you can actually see a rainbow just like in this picture. So how are rainbows formed? Let's look at this picture. You've got the sunlight, so usually most rainbows are formed where you have the sunlight behind you or right above you. You've got a ray from the sun coming in, and let's look at this droplet here. When it goes from air to water, it's going from a faster medium to a slower medium, so it refracts. It's going to bend toward the normal. Now, each color of light bends a different amount. It's due to the frequency and wavelength of those colors. But you can see here, red is going to bend the least, and blue and violet are bending the most. So they start to separate in there. Now, if this droplet is in just the right position, when this light hits the back of it, it will exceed the critical angle, and then you get total internal reflection. So all these colors reflect towards the front of the droplet again, where when they leave the droplet, they're going to refract again, and the colors separate even more. So from this droplet, this sad looking guy, I don't know why he's sad, he's looking at a rainbow, he's only going to see red from this droplet. That's it. And there's going to be a bunch of droplets in this area that he's going to see red from. And then this droplet down here, the only color he sees from it is the violet. These others are going to go below his line of sight. And then you'll have all these millions and millions of droplets in between, giving you all that Roy G. Biv. So that's how you see the complete rainbow. Now, each person is going to see a slightly different rainbow because even if you're right next to each other, you're going to have a slightly different angle at those water droplets. So every rainbow you see is your very own rainbow. Fiber optics, you've probably heard about that before. A couple of most common uses for fiber optics is, first of all, data communication. So like your cable TV has a copper cable going to it probably. Well, it could have a fiber optic cable. Another use for fiber optics is in surgery. I've had a couple surgeries where the doctor used a very tiny camera to insert into the surgery on my hip, into the hip area, so you could see what was going on. And the signal from the camera to the monitor was communicated through fiber optics. Now, what a fiber optic is a very thin glass fiber that just sends light through it. Now, you've probably seen it before, like one of these things, one of these toys. I don't even know where we got this, but you see the fibers, you don't see the light in the fiber itself, but I can bend it and you see the light coming out of the fiber. So how do these things bend the light? Well, let's look at that.
And here's another demo that's easy enough to do at home. All you need is a plastic bottle, some water, and a laser pointer. Now, with the bottle, you do need to puncture a small hole in it. I've got a hole drilled right down here towards the bottom, and that's all you need. All right, I'm going to aim the laser pointer horizontally through the bottle. I'm going to aim it at the hole right where the water stream is going to come out. Okay, now up near the bottle, up in here, we don't see anything. No light is escaping there. We've got total internal reflection. Farther down the stream, the light is starting to break apart. The water is starting to break apart, so the light is able to escape down there. But up here where that flow is smooth, we don't see any of that water escaping, just like a fiber optic cable works. Okay, one more time, a little closer up. I've got coffee creamer in there to cloud up the water so we can see the laser going through it. Let's watch this one. Look at that. You can see the light reflecting back and forth inside the stream of water. That's total internal reflection. It's just like what a fiber optic cable would look like on the inside. Bending that light straight down into the sink.
It's that total internal reflection again. So let's take a look at a picture. Here we've got the glass fiber, that's the center part here, and then covering that is called this cladding. And the glass fiber has a higher index of refraction. This cladding around it has a lower index of refraction. These glass fibers are very small in diameter, like your hair. Yet with all this cladding around it, you could tie it in a knot and it still stays intact. So the idea is the light comes in, and because these fibers are so thin, when it hits the wall here, ideally it's going to be greater than that critical angle, and you get total internal reflection. And it keeps doing that as it travels the length of the wire there. So one advantage is it's fast. It's the speed of light. It's a very strong signal as well, because the light, it just blinks on and off, in certain sequences, and then the end reads that. But it's a very good signal because the light's either on or off, so you get a good signal quality for that. It's very expensive, though. That's one of the downsides. You won't see it in a lot of houses yet because of that, but it is a very reliable signal. There is a video that it goes in a little more detail in this, and I'll put a link right up there. You should check that out if you're interested in this. They talk about putting a fiber optic cable connecting continents across the ocean floor. It's really cool. They can make them really long like that. Now, you can have more than one signal traveling through the cable at once. For example, if this was a phone line, you could have thousands of people on that same fiber optic cable. What they do is each user would have a different frequency of light. So yeah, a different color. You might be talking with a green color light, somebody else might have a blue color, and you've got all the shades in between. So that's fiber optics, and you can make one at home with that demo. Eyeglasses are next. This is the one that might mean the most to you. If you have bad vision, you've got glasses or contact lenses, this is going to explain kind of how they work. In a normal eye, we all have a lens in the front of our eye, a converging lens. Somebody with good vision, these light rays will converge right at the back of their eyeball, the retina. When that happens, you'll have a clear image there. If they converge before or beyond that, you're going to go get a blurry image. For nearsighted people like me, I can see things well up close, but things far away are pretty blurry. So the lens is actually converging the light rays too much. So you need to separate the light rays a little bit. So you're going to use a diverging lens. So if you're nearsighted, you can feel the lens of your glasses. It should be thinner in the center, thicker at the edges. And this spreads the rays out a little bit before it gets to your lens, and then your lens converges them back on the retina. You see a clear image. Somebody who's farsighted, like my daughter, she sees things far away well, but up close it's a little blurry for her. So that lens in her eye is not converging enough. So you need a little help there. So you put a converging lens in front of it to converge it a little bit before it gets to your lens, and then you get it focused on your retina like that. One more image showing the same thing. I just like this one because it's got a person here. Now, these aren't really ray diagrams because the rays are coming from two different spots, the head and the foot. But if you notice, the image here is upside down. That's right. A lot of you probably already knew that, but we actually see things upside down. Wouldn't that be weird if we were stuck looking like that? But anyway, our brains early on in life learned that that was not a good thing. So our brains flip that image so we see it properly. I've read about studies where people wear these special glasses with the lenses, converging lenses, that flip the image upside down. And they'll wear it for a few days, seeing things upside down, but then all of a sudden their brain recognizes that and flips the image and they see things right side up. The problem then is they take the glasses off and they see everything upside down. That'd be a little scary, but their brain quickly adjusted to that and flipped the image again. So it's kind of wild that your brain is doing things without you telling it to. Okay, a telescope. This is the last one we're going to look at. There's a lot of different types of telescopes. I just picked this image because it was a good image. You've got light coming in from the moon or a planet, whatever you're looking at. And then you've got a converging mirror back here. So like I said, different types of telescopes, they use different optical instruments in them. So this one has a converging mirror. So it's a lot like when I burned the piece of paper with a converging mirror. If we just held a sheet of paper in the sunlight, it wouldn't burn. But we take that mirror and we concentrate all those rays in one spot, then you can get that light energy like that. So our eyes are not very big. The pupil's not very big. So this allows a bigger, more light to come in basically. And then that light gets focused here. You've got a mirror that will reflect it to the eyepiece. And then you've got a converging lens here, basically a magnifying glass that magnifies that image. So that's one way a telescope works. A camera, I should go back to the eyes for the camera. A camera is working a lot like an eye. You've got the lens of the camera and then it focuses the image on the back. The old days, we called that film. Now it's all digital. But there we go. There's a telescope. Pretty interesting to see that. So I talked about a few things here. Certainly, if anything piques your interest, I encourage you to do a little more research on it. But I hope you learned some things.